Okay, folks, let's keep going down the rabbit hole. We are now going to solve the Schrödinger equation for the particle on a ring problem. This will be very analogous to our particle in a box, except for our boundary condition is that of a ring. So let's go for it. And this one will actually be much more straightforward than what we've seen in the past. So setting up our physical picture, we are going to confine our particle to just the XY plane for now. So there it is. There's our particle with mass m. And on this ring, we're going to say that it has a constant and 0 potential energy. So noting here that we've now are moving our particle in 2 dimensions, x and y, our kinetic energy operator gets a little bit more complicated, as you can see. And so we can replace that with del squared. And now noting that at this point it becomes much more useful for us to go to spherical coordinates instead of Cartesian coordinates, we can transform del squared into its spherical coordinate space. And given that we're only dealing with the xy dimension, we only see dependencies on phi. We can also do another thing to make this problem a little bit more straightforward for the time being, and that is to call the radius a constant. So for now, we're not letting this particle like oscillate in and out of that ring. Rather, we're just confining it to that ring. So what that means, our operator here is going to become a lot easier to deal with. If we have a constant radius, then this second derivative drops out to 0. This first derivative drops out to 0. And then the only terms we need to keep are right there. So I can rewrite my Hamiltonian simply as negative h bar squared over 2m. And now I've got to tack this on. There's going to be an r squared on the bottom and second derivative in phi. And we might recognize that quantity mr squared is our moment of inertia. So we can simplify that even further and rewrite our Schrödinger equation as the following. Okay, so we can now set this up in our nominal ansatz method. So let's go for it. I'm going to rearrange the equation and push all the constants through so I can get into the standard reduced form. So that's going to look something like this. Second derivative in phi. And now that's going to go plus 2ie over h bar squared times psi equals 0. So we can make our standard guess of psi being e, and I'm going to call it to the a, and phi is now our dependency there. And straight away we could go to the second derivative in phi of that as a squared e a phi. Beautiful. And plugging it all in, continuing along with our ansatz method. So that's our second derivative. And now we're going to have 2ie over h bar squared e to the a phi all equals 0. We can eliminate the e to the a phi, and we can see right away, hopefully, that this is going to give us imaginary solutions, right? So now if I take the square root of both sides, I get a will be, let's see, for now I'm just going to write that as square root of negative 2ie over h bar squared. So we're going to get an imaginary number. And maybe you might recognize this from our previous video, but this quantity, 2ie over h bar squared square root, is ml, the new quantum number that we came up with. So we can say that a equals plus or minus I ml, and thus my general solution for psi of phi will look like the following: a e I ml phi plus b e negative I ml phi. And if you recall, in the particle in a box, we described this as, you know, particles moving from left to right and particles moving from right to left. But based on the picture that I have here, right, following my right-hand rule, we recognize that we're really only going to be moving in one direction depending on our orientation of our angular momentum. So I'm going to throw out one of those solutions and recognize that we really only need one of them because we've already allowed ML to take on plus or minus values. So we have our general equation right there, our general solution, and now we're ready to normalize it. And I'm just going to keep it going. Let's normalize this sucker. So we came up with the following. We said psi equals A, E, I, ML phi. So now putting in our normalization condition, which says we'll have some normalization constant, n squared, times psi star psi, and only dependent on d phi, which goes from 0 to 2 pi, and all of that equals 1. And hopefully you can see what's going to happen here. We're going to have n squared integral from 0 to 2 pi. My psi star is e to the negative I ml phi. Psi is e to the positive I ml phi d phi. And hopefully what we can see is this product is going to equal 1. And so then when I take the integral from 0 to 2 pi of just d phi, that's also just going to give me 2 pi. So I'm going to end up with 2 pi n squared equals 1. And thus my normalization constant is 1 over root 2 pi. So finally I can say my specific solution for psi of phi of the particle on the ring problem is 1 over root 2 pi e to the I ml phi. Beautiful, simple little wave function there. So now we need to test if it satisfies the cyclic boundary conditions. So here we have our wave function. And recall, our cyclic boundary condition, said the following: we have to start and stop at the same place over our 2 pi radius. So that's what it looks like in this 1D world. In our actual, 3D world, it might look something like this, where the particle is oscillating on this ring. And if I drew this correctly, yes, there it ends where it started. So the condition that we need to test is, does psi of phi equal psi of phi plus 2 pi? So let's go for that. So I'm going to leave psi of phi here. And then now we'll place phi plus 2 pi into the value of phi. So that's going to go 1 over root 2 pi e to the I ml phi. And I'm going to put all of that into parentheses, phi plus 2 pi. Okay, so now let's separate that out. Psi of phi equals 1 over root of 2 pi. And I'll distribute these through and separate them based on their exponential properties. So that becomes e to the I ml phi times e to the I ml 2 pi. And now we can begin to play around a little bit. So for one, we can see that first quantity, this 1 over root 2 pi, e I ml phi, that's just the same as psi of phi. There's another trick that I can make from the Euler relations, and that's the following. E to the I pi equals -1. So I can replace the e to the I pi with -1, and then that's raised to the 2 ml power. I can divide both sides by psi of phi, and I get 1 equals -1 raised to the 2 ml power. And now if we were to start testing those values of ml that we came up with, hopefully you can see it's going to satisfy this relationship. So for example, if I put +1 in for ml, -1 squared is +1, so that works well. Well, what if I put -1 in there? Well, that becomes -1 raised to the -2 power. That still equals 1. So that's all good. And as you might guess, we could keep plugging in our other integers, and those will satisfy this relationship. You might also see there's another solution for ML that we didn't come up with before, and that's ML equals 0, right? I could plug a 0 in there, and that will satisfy this relationship. So not only do we prove that our solution satisfies the cyclic boundary conditions, but we gained one more requirement for our quantum number. So ML can be 0, plus or minus 1, plus or minus 2, plus or minus 3, etc. Okay, so one last final detail to talk about in this video. So where is the particle on this damn ring? So we can begin to answer that question by looking at the square modulus, right? Recall when we look at psi squared, that gives us the probability distribution. And so if we compute that, if we put that together, then we'll end up with the following, right? So that's going to be psi star psi, okay? So we'll note that the square modulus is now going to equal 1 over root 2 pi e. And remember, the square modulus goes psi star psi. And we have an imaginary number in there, so we have to do the complex conjugate. So e to the negative I ml phi, so that's my psi star. And now we can multiply it by psi, 1 over 2 pi e to the positive I ml phi. And hopefully what you can see here is the e's are going to cancel, and I'm just going to end up with 1 over 2 pi. So this is a really curious result, because what we get out of this thing is no phi dependence. We're saying the square modulus is just this constant value, implying that the particle can really be anywhere on the ring with equal probability. So there's some consequences of that. The probability density is independent of angle phi. Therefore, the probability of finding the particle somewhere on the ring is indefinite. Precise knowledge of the angular momentum eliminates the possibility of precisely knowing where the particle is located. Thus, angular momentum and angle create a set of complementary observables suspect to Heisenberg uncertainty principle. We are going to have to deal with that soon, but for now, we're going to continue down the rabbit hole of looking at this problem. And on the next video, we're going to look at the particle on a sphere. And then in the coming lectures, we're going to have to deal with this Heisenberg uncertainty issue between angular momentum and angle. Okay, thanks, folks. I'll see you in the next one.